I want you to imagine something you might have done just this morning, or maybe last week. Picture yourself driving up to a DC fast charging station.
Right.
You park, you pop the charge port open, and you grab that really heavy, thick black cable off the holster. It's got some serious weight to it,
Yeah,
right?
they're definitely not light.
Exactly. So you line it up, push it into your car, and you hear that satisfying, heavy, mechanical click. Maybe you tap your phone to pay, grab a coffee, and just sit back while the battery fills up. I mean, it is a completely mundane, everyday action. You don't even think twice about it.
No, you really don't.
But beneath that simple action, beneath that mechanical click, is a terrifyingly high stakes, microsecond by microsecond conversation happening between your car and that charger. And if that conversation stops, even for a tiny fraction of a second, the results could just be catastrophic.
Yeah, it is entirely visible to you, the user, and honestly, that is exactly how it's supposed to be. I mean, you shouldn't have to think about the sheer volume of engineering required to make that simple click safe. But the reality is that the moment you plug in, you are initiating a highly volatile electrical event.
Yeah.
You're connecting this massive external power source to a dense chemical energy storage system.
Okay, let's unpack this, because inside that high voltage architecture is a hidden protocol known to engineers as 506 U019B.
That's the one.
It is a highly specific, incredibly critical fault protocol. And to understand it, we're stepping into what engineers refer to as the high voltage battery system's fifth dimension.
The fifth dimension, yeah.
Right, which sounds totally like a sci-fi concept, but it's the system high voltage execution and global safety layer. It is the literal bedrock of electric vehicle safety. Because when you fast charge an EV, the normal computer systems in the car, like the ones that handle the radio, the wipers, the normal driving dynamics, they kind of just step back.
Exactly. They get out of the way.
Right. And the battery management system, the BMS, essentially bypasses those normal controls and opens a direct, unmediated line of communication to the external charger.
And that direct line is, well, to everything. This isn't just about, sending a battery percentage to the screen so you know when you can drive away.
No.
This is a closed loop, literal life or death data exchange. The charger on the outside is capable of pushing massive, massive amounts of energy. We are talking hundreds of amps, potentially 800 or even 1,000 volts.
Which is huge.
It is. And the charger itself is fundamentally kind of dumb regarding the battery's internal state. It only does exactly what the car tells it to do.
Right.
So without this precise, constant communication, there is nothing stopping the charger from pumping extreme energy into a battery that is full or too hot or damaged.
And if that happens, you get severe overcharging, which leads directly to thermal runaway.
Yes, the worst case scenario.
For anyone who isn't steeped in battery chemistry, thermal runaway is sort of the polite engineering term for a battery catching fire and burning so hot and so fast that it creates its own oxygen.
Yeah, you could dunk it in a swimming pool and it will just keep burning.
Which is terrifying.
Yeah.
So the stakes are literal life and death. And the 506 U019B fault is the system's way of screaming that this critical communication line is broken.
Exactly.
It triggers when the battery management system in the car and the external fast charger just lose communication. They time out. They stop talking. So let's dig into the physical reality of this. What actually causes that communication to drop? Because if we look at the root causes, the physics of failure, we see two main villains.
Right.
The first one is a combination of overvoltage, which is known as EOS, and electrostatic discharge, or ESD.
Yeah, to really grasp this, we have to think about what happens the exact moment you push that plug into the socket. You aren't just snapping together a clean piece of plastic.
No, not at all.
You are dealing with a massive high-voltage circuit coming into contact with another high-voltage circuit. So in the split second that the heavy contactors slam shut, or the moment the pins make physical contact, you generate a highly violent electrical environment.
Wait, when you say contactors, we're talking about the heavy-duty mechanical relays inside the battery pack, right? The physical switches that connect the battery cells to the outside world.
Exactly. When those heavy metal plates slap together to close the circuit, they don't do it cleanly. At a microscopic level, the metal actually bounces.
Oh, wow.
Yeah, and as it bounces, high-voltage electricity jumps the microscopic gaps, creating these high-energy transient spikes. But even before that, just the act of walking up to the charger and holding the cable can be dangerous.
Wait, seriously?
Oh, yeah. Think about walking across a synthetic carpet in the winter and touching a doorknob. You
Yeah.
get a static shock, right?
Right, the triboelectric effect. You've built up a surface charge.
Yeah, exactly. Now imagine you are holding a heavily shielded charging cable, dragging it across concrete wearing rubber-soled shoes.
Oh, man.
Yeah, you can easily build up thousands of volts of electrostatic potential. So the moment the metal pins of the charger get close to the metal receiver pins in the car, that static electricity discharges right into the communication pins.
It's like a microscopic lightning bolt.
A literal lightning bolt on a micro scale.
Yeah.
And the hardware on the other side of those pins isn't a heavy iron anvil. It's a delicate silicon microchip.
Right, the transceiver.
Specifically, yeah, a CAN transceiver or a PLC powerline communication transceiver. And these chips are designed to operate on tiny, delicate 3-volt or 5-volt logic signals. If an electrostatic discharge hits them just right, or if a massive overvoltage spike from the contactors overwhelms the line, they suffer what is called electrical overstress, or EOs.
So the chip just, what, burns out?
It is more violent than that.
Really?
Yeah. The thousands of volts from the ESD spike will find the path of least resistance through the silicon junction of the transceiver. And because the energy happens in nanoseconds, the silicon literally vaporizes locally.
You're kidding.
Nope. You blow a microscopic crater right into the semiconductor material. The circuit is permanently, physically destroyed. The pathway is gone.
That is terrifying. I mean, just the static electricity from your jacket could theoretically vaporize the communication chip.
It absolutely could.
But there is a second root cause here, right? And it's much slower, but just as deadly. It's called fretting and contact resistance. We are talking about long-term, high-frequency plugging and unplugging, physically wearing down the metal plating on the charging terminals.
Yeah, and the physical metallurgy of those pins is fascinating. To maintain excellent conductivity, the heavy copper pins in the charging port are typically plated with silver or gold.
Because they don't rust, right?
Right. These noble metals don't oxidize easily, and they provide incredibly low electrical resistance. But every single time you push that heavy plug into the socket, you are scraping metal against metal.
Like sandpaper.
Kind of, yeah. Over time, that wiping action wears through the micron-thin layer of silver or gold, exposing the base copper or brass alloy underneath.
And once that base metal is exposed to the oxygen in the air, it starts to oxidize. It rusts, essentially.
It does. But the real killer isn't just plugging it in and out. The real killer is what happens while the car is sitting there charging.
Well, it's just parked?
Yeah, it's called fretting corrosion. Imagine your car is plugged in at a station near a busy highway. Heavy trucks are driving by, causing low-frequency vibrations in the concrete. Or maybe it's a really windy day, and that thick, stiff, heavy black charging cable is acting like a sail, catching the wind and slightly tugging on the port.
So the plug is like microscopically wiggling inside the socket?
Exactly. We call it micromotion. We are talking about movements on the scale of 10 to 100 micrometers. It's totally invisible to the naked eye. But at the microscopic level, the surfaces of the pins are grinding against each other.
Oh, wow.
And this continuous tiny grinding action generates heat and continually breaks up any thin oxide layer that forms. That exposes fresh metal, which then immediately oxidizes again. Furthermore, the debris from this grinding gets trapped in the microscopic valleys of the metal surface.
So it's grinding itself into dust, and the dust is getting trapped inside the connection.
Exactly. And because there is electrical current passing through this chaotic, dusty, vibrating microscopic landscape, you get something called microarc oxidation.
Microarcs, like sparks.
Yes, tiny, invisible sparks jump across the vibrating gaps, literally burning the metal and the debris. The metal surface actually blackens. If you ever look closely at a heavily used charging plug and see dull black pitting on the pins, that is microarc oxidation.
And I imagine that black burnt metal is not a very good conductor of electricity.
It is a terrible conductor. It basically acts as an insulator, or more accurately, a highly variable resistor. As that black oxidation layer builds up, the clean, crisp, digital signals trying to pass between the car and the charger get distorted. Digital communication relies on sharp, square waves of voltage-crisp transitions from 0 to 5 volts to represent the ones and zeros.
Okay, hold on. I'm stuck on something here.
Sure.
I understand that the black oxidation creates resistance. But we live in the 21st century. Software and digital systems are incredibly robust. If it's just a bit of resistance on the pin, why does the signal completely drop? Why doesn't the car's computer just boost the voltage of the signal? Just shout louder over the resistance to push the signal through the dirt?
That is a great question, and it really speaks to the fundamental divide between software logic and hardware physics.
Mm.
First of all, the communication protocols operate on strict international physical layer standards. You can't just arbitrarily increase a 5-volt logic signal to 20 volts without frying the receiver on the other end or, violating the standard entirely.
Oh, right, because it expects 5 volts.
Exactly. And second, resistance caused by fretting isn't just a simple block to the signal's volume. It actually changes the entire electrical characteristic of the line.
What do you mean by that? It changes the characteristic.
So when you add that unpredictable resistive oxidation layer and you combine it with the natural capacitance of the long, thick charging cable, you create an unintended RC circuit, a resistor-capacitor circuit.
Okay.
This physically changes the timing of the line. Those crisp, square digital waves we talked about. The increased resistance slows down how fast the voltage can rise and fall. So the square waves turn into sloppy, rounded shark fin shapes.
Oh, I see. So it's not just that the signal is quieter, it's that it's slurring its words.
Perfectly said, yes. The receiver, on the other end, is looking for a sharp voltage transition at a very specific microsecond. If the wave is rounded off and delayed because of the fretting resistance, the receiver completely misinterprets the ones and zeros. The data just becomes gibberish. And once you have extreme impedance from fretting or a physical open circuit from electrostatic discharge blowing a crater in the chip, no amount of software shouting can cross that physical gap. Software is, ultimately, just electricity moving through physical pathways. If the bridge is out, the signal cannot cross.
The bridge is out. Man, that paints a very clear, very grim picture. A burned-out pin or a highly oxidized terminal isn't just a broken wire, it's a blinded battery.
It is.
It leaves the massive high-voltage charger totally blind to the battery's real state of charge, its internal cell temperatures, and its voltage limits. It might just keep pushing massive current blindly into a battery that is about to boil.
Which is exactly what we want to avoid.
Right. So if we accept that the physical hardware is constantly under attack and those metal pins are inevitably going to degrade or fail, what happens in the exact millisecond the electrical bridge drops, there has to be a fallback system.
There is, and this is where the architecture of the fifth dimension really flexes its muscles. Because engineers know the physical hardware can and eventually will fail, the software architecture operates on a posture of constant paranoia.
Constant paranoia. I like that.
It really does. It assumes failure is always imminent, and it is ready to act instantly.
Right. And this invisible software defense mechanism relies on continuous heartbeat checks. It's called E2E, or end-to-end protection.
Exactly.
The car and the charger are constantly pinging each other, like a relentless back and forth verifying the demand voltage, the maximum allowed current, and the real-time temperature. But they aren't just sending simple plain text numbers. The protocol uses rolling counters and something called a CRC8. Let's break that down, because this is the mathematical shield against that electrical noise, right?
Yeah, so we established that the environment inside the charging cable is incredibly noisy electrically. You have high voltage switching, magnetic fields, and fretting resistance distorting the signals.
Right.
So imagine the car wants to tell the charger, please deliver 100 amps. In binary code, that message is a specific string of ones and zeros. But as that string travels down the wire, a burst of electromagnetic voice from the charger's internal transformers induces a tiny parasitic voltage on the communication wire.
A spike.
Yes, and that little spike of noise hits right as a zero is passing by and pushes the voltage up just enough that the receiver misreads it as a 1.
So a single bit gets flipped by the electrical noise.
Exactly. And flipping a single bit can change the binary value from 100 amps to 400 amps. If the charger blindly obeys that corrupted message, it will destroy the battery.
Oh, wow.
To prevent this, the engineers implemented E2E protection. Every single message has a rolling counter. This is simply a number that increments with every single message 1, 2, 3, 4, 5. This prevents the system from acting on an old frozen message that got stuck in a buffer somewhere. If the charger receives message number 45, and the next message is also 45, it immediately knows something is wrong and ignores it.
Okay, so it prevents the charger from getting stuck in a loop. But what about the bit flipping? How does the CRC8 stop the charger from misinterpreting a corrupted demand?
CRC stands for Cyclic Redundancy Check. The 8 means it's an 8-bit checksum. This is the true mathematical genius of the protocol. It is not just a simple matter of adding up the numbers in the message. It uses a mathematical process called polynomial division.
Polynomial division.
Yeah. Before the car sends the message, its processor treats the entire string of ones and zeros as a giant polynomial equation. It then divides that massive equation by a predetermined fixed divisor, basically a secret mathematical key that both the car and the charger know.
I'm trying to visualize this. It's sort of like doing long division, but with binary code.
That is exactly what it is. And just like long division, you usually end up with a remainder. That remainder is the CRC8 checksum. The car attaches that specific remainder to the very end of the message and sends it across the noisy wire.
Okay, I follow.
When the charger receives the message, it strips off the checksum, looks at the main data, and performs the exact same polynomial division using the same secret key.
And if the remainder the charger calculates matches the remainder the car sent, it knows with near absolute mathematical certainty that not a single bit was flipped in transit.
Precisely. If even one single zero was changed to a 1 by electromagnetic noise, the polynomial division will yield a wildly different remainder. The charger will see that its answer doesn't match the car's checksum, and it instantly realizes the data is hallucinated garbage.
And it just tosses it out.
It discards the message entirely. And this complex math is happening on every single heartbeat pulse, hundreds of times a second, just to guarantee that the two systems are acting only on perfectly clean, uncorrupted reality.
Okay, so the system is paranoid, and it's doing extreme math to verify every whisper. But what if the whisper stops entirely? What if the CLC checks keep failing, or that oxidized pin we talked about finally creates a total open circuit? The heartbeat stops. That is the moment the U019B fault becomes active. And it triggers what the engineering architecture calls the failsafe. And from what I understand, this process is breathtakingly fast.
Oh, it has to be. The moment communication drops, or a heartbeat is missed and cannot be verified, an internal countdown begins. The battery management system in the car has exactly 500 milliseconds, half of 1 second, to trigger the failsafe.
In that 500 milliseconds, what exactly has to happen?
The BMS must execute a flawless emergency shutdown. First, it must command the heavy DC fast charge contactors to physically snap open, physically severing the high-voltage connection between the battery and the outside world.
Okay, step one.
Second, it must lock the charging port actuator so you, the user, cannot pull the cable out.
Right.
And third, it must throw a severe fault light on the dashboard and record the U019B code. All of that mechanical and software execution must be completed before half a second expires.
Why half a second? Let's dive into the chemistry of that. What is the catastrophic event that is waiting at the 501 millisecond mark?
The primary enemy here is a phenomenon called lithium plating.
Okay.
When you are fast charging, you are forcefully driving lithium ions from the cathode, through the liquid electrolyte and into the graphite structure of the anode. This process is called intercalation. You can think of the graphite anode like a highly structured parking garage, and the lithium ions are cars trying to find a parking spot.
Makes sense. Fast charging is like a rush hour traffic jam trying to get into the garage.
Exactly. When the battery is empty, there are plenty of spots, and the ions can intercalate quickly. But as the battery gets full, the parking spots fill up.
Right.
The BMS constantly monitors this and tells the charger to slow down to reduce the current so the ions have time to find a spot.
Right.
But if the communication drops and the charger is still blindly blasting 300 amps into a nearly full battery, those ions arrive at the anode way too fast.
They have nowhere to go.
They can't get into the graphite structure. So instead of intercalating, they start piling up on the outside surface of the anode.
They just stack up outside the garage.
Yes, and as they stack up, they transform from ionic lithium back into solid metallic lithium. This is lithium plating. And metallic lithium doesn't grow in smooth, flat sheets. It grows in sharp, microscopic, needle-like structures called dendrites.
Oh, needles. That sounds bad.
It is. If the blind charging continues, these metallic needles grow longer and longer until they physically puncture the thin plastic separator that divides the anode from the cathode.
And if they puncture the separator, the positive and negative sides of the battery physically touch?
And you get a hard internal short circuit. The massive energy stored in the cell dumps all of its heat into that tiny microscopic point. The liquid electrolyte boils, the internal pressure spikes, the cell vents toxic gas, and the extreme heat triggers the neighboring cells to do the same.
Thermal runaway.
Exactly. That is thermal runaway. The 500 millisecond window is the absolute maximum time the battery chemistry can endure that blind, high current rush hour before the dendrites begin to form and cause permanent, dangerous damage.
I see. That paints a vivid picture of the microscopic daggers growing inside the battery. But, I have a fundamental question about that timeline.
Okay.
You say 500 milliseconds is the maximum time to prevent a fire. To a human, half a second is incredibly fast. That's a blink of an eye. But in computing, where processors operate in nanoseconds, and where they are doing complex polynomial division hundreds of times a second, 500 milliseconds, is an absolute eternity.
And it really is.
The computer knows the signal is dead in 1 millisecond. Why wait half a second? Why not snap the contactors open in 10 milliseconds, the exact moment a single CRC checksum fails?
That is the eternal struggle between theoretical safety and real-world usability.
Yeah.
If we lived in a perfect vacuum, yes, the system would shut down in 10 milliseconds. But the real world is incredibly messy.
Messy how?
Well, we talked about fretting and vibration earlier. If the car cut off the charge instantly at the slightest hint of noise, or the exact moment a single data packet dropped due to a tiny voltage spike, charging a car would be practically impossible.
Really? Just from a little noise?
Oh yeah. Every time a heavy truck drove by the station and vibrated the concrete, the micromotion would distort a single square wave, the COC would fail, and your charge would abort. Every time a nearby power line surged, your charge would abort. You would be walking out to your car, unplugging it, plugging it back in, and restarting the session on your phone 20 times an hour.
Oh, wow. Yeah, you would hate the car.
You would completely hate it. So the 500 milliseconds isn't just a delay, it's a deliberate, calculated buffer.
Okay, so it uses that eternity to evaluate the situation.
Exactly. It provides a tiny window to see if the communication recovers. The software is programmed to tolerate a 3 to 5 cycle packet loss. If it misses 1 heartbeat, it waits. If it misses 2, it prepares. If it misses 3, 4, 5, it knows this isn't just a passing truck. This is a real U019B fault.
The bridge is truly out.
Right. And only then, right before the lithium plating reaches a critical threshold, does it drop the guillotine and sever the connection.
A deliberate pause to prevent false alarms while still respecting the absolute chemical limits of the battery. That is brilliant engineering. But there's another fascinating layer to this safety net.
Oh, yeah.
Once that guillotine drops and the charge is aborted, you might think you could just pull the plug out and drive away. But the architecture highlights a standardized, safe power-down procedure, specifically focusing on a rigid rule called no-load release.
Right.
It states that the electronic lock holding the charging cable to the car cannot physically release until the current flowing through the lines drops below an absolute safety baseline of 1 amp.
And this rule has absolutely nothing to do with battery chemistry. This is strictly, unequivocally designed to protect human life from a phenomenon called a DC arc flash.
Let's explore that. What is the actual physics of a DC arc flash? Why is pulling a plug so dangerous?
To understand this, we kind of have to look at the difference between alternating current, AC, and direct current, DC. The electricity in your house is AC. It naturally oscillates. The voltage goes from positive down to 0 to negative and back up 60 times a second.
Okay.
Because it constantly passes through 0 volts, if you unplug a vacuum cleaner while it's running, any tiny spark that tries to jump the gap is instantly extinguished the moment the AC voltage hits 0.
It naturally turns itself off 60 times a second.
Precisely. But fast chargers use direct current. DC never crosses 0. It is a continuous, relentless wall of energy pushing in one direction. Imagine you're pushing 200 amps of direct current through that heavy cable into the car. If there was no mechanical lock and you got impatient and forcefully yanked that live high current plug out of the socket, the electricity wouldn't just politely stop flowing.
It wants to keep going.
It does. Direct current has an immense amount of electrical inertia. As the physical metal pins separate, the 800 volts of potential energy will literally tear electrons right out of the oxygen and nitrogen molecules in the air between the plug and the socket.
It rips the air apart.
It ionizes the air. It turns the air itself into a conductive plasma channel. The electricity jumps the physical gap you just created, sustaining the circuit through the air.
Yeah.
This creates a brilliantly bright, incredibly energetic arc of lightning right at your hands.
That sounds like an industrial plasma blowtorch.
That is precisely what it is. A DC arc flash is one of the most violent electrical events imaginable. In a fraction of a second, the temperature of that plasma arc can reach upwards of 35,000 degrees Fahrenheit, which is hotter than the surface of the sun.
Oh my God.
The intense heat instantly melts and vaporizes the copper pins in the plug, causing an explosive expansion of metal gas. If you were holding that plug, the arc flash would severely burn your hands and arms, the brilliant flash of ultraviolet light could permanently blind you, and the molten copper could cause horrific shrapnel injuries.
That is absolutely horrifying. So the electronic lock isn't just a convenience feature to keep people from stealing your cable. It is a life-saving mechanism.
It is literally holding the cable hostage to save your life. Even if there is a massive U019B communication failure, even if the computers are screaming, even if you are frantically pressing the unlock button on your keys because you are late for a meeting, the global safety layer overrides everything.
Wow.
The car relies on raw, analog hardware sensors to measure the actual physical current flowing through the heavy copper lines. It will not, under any circumstances, release that mechanical actuator until it is mathematically certain that the current has decayed to below 1 single amp. The danger of an arc flash must be 0 before you are allowed to touch that plug.
It's holding the cable hostage to save you from yourself. I love the sheer, uncompromising rigidity of that.
So we've established that the physical pins are highly vulnerable to fretting and electrostatic craters. And we know the software has this incredibly tight 500 millisecond safety net, using polynomial division to catch errors and holding the plug hostage to prevent an arc flash.
Right. But that leads to the next logical step in the architecture. If we know the software needs impeccably clean data and nanosecond timing to execute the failsafe, how do engineers actually design the physical circuit boards to survive the noise and the chaos of 800 volts of electricity happening right next door?
Yeah, this takes us deeply into the realm of DFMEA design failure mode and effect analysis. In engineering, before you ever build a prototype, you sit down and analyze every single way a component could fail, and you rank those failures by severity. The U019B communication fault naturally carries a very high severity rating because it blinds the overcharge protection.
Yeah, the documentation rates the severity of a standard communication drop at a 7 out of 10.
Hmm.
But it notes that the rating immediately leaps to an S.8 or S.9 if the design analysis considers the subsequent thermal runaway and the arc flash risks we just discussed.
Right.
And just for context for you listening, an S.9 or S.10 in automotive engineering usually implies death or severe injury without warning. So an S.9 rating means the engineers are treating this as an apocalyptic scenario. They cannot afford a single flaw.
Extremely high stakes. And to prevent an S.9 disaster, they have to build an impenetrable electrical fortress on the circuit board itself. The first and most critical wall of that fortress is called galvanic isolation.
Galvanic isolation.
This is an absolute requirement under the ACE-LD safety standard, which is the highest possible level of automotive safety integrity. They mandate the use of high-precision digital isolators or high-impedance transformers rated for over 3,000 VARMs to physically block noise.
Okay, we need to break down galvanic isolation. How do you pass data between two systems without actually connecting them?
Well, to understand why it's necessary, imagine the high-voltage system, the giant external charger pushing 800 volts and hundreds of amps, as a massive, incredibly loud industrial rock concert.
A rock concert, okay.
Inside that charger, heavy-duty insulated gate bipolar transistors, or IGBTs, are violently switching alternating current into direct current thousands of times a second. This violent switching generates massive electromagnetic waves called common mode noise.
So the high voltage is throwing off massive amounts of electrical interference.
A deafening roar of electrical noise. Now imagine the low-voltage control board, the car's BMS computer, which operates on tiny, delicate 3-volt logic signals, as a very quiet library.
Right.
If the high-voltage rock concert and the low-voltage library share the same physical ground wire, the noise from the concert will travel straight down that copper wire and completely drown out the quiet whispers of the computer chips. The noise would flip every bit, fail every CRC check, and permanently paralyze the computer.
So you have to separate the grounds. You have to build a wall.
Exactly. Galvanic isolation is literally an electrical moat. There is no physical conductive wire connecting the high-voltage measurement side to the low-voltage logic side. The circuit board is physically split in half. To pass the critical communication data across that gap, they use something like an optocoupler.
An optocoupler. Wait, using light to send the signal?
Exactly. On the high-voltage side, the electrical signal is fed into a microscopic LED. The LED blinks on and off, translating the ones and zeros into pulses of light. That light shines across a tiny physical gap inside the chip and hits a phototransistor on the low-voltage side.
Wow.
Yeah, the phototransistor sees the light and turns it back into a clean 3-volt electrical signal.
That is brilliant. It's a 3,000-volt rated soundproof glass wall between the rock concert and the library. It allows the visible data, the blinking light, to pass through effortlessly, but it physically blocks the destructive high-voltage acoustic noise from infecting the brain of the car.
It's an impenetrable barrier. You can have a 2,500-volt transient spike hit the high-voltage side, and the low-voltage brain on the other side of the optocoupler won't even feel a tickle.
Okay, so the soundproof glass wall stops the continuous roar of the charger, but Earlier, we talked about electrostatic discharge, the sudden, violent lightning strikes when you first push the plug in.
Right, the ESD.
How does the board survive a 10,000-volt static shock hitting the pins directly? The architecture mentions TVS clamping and anti-bounce mechanisms. It specifically cites the use of low junction capacitance bidirectional TVS diodes and a second-order RC low-pass filter on the communication lines.
Right, so the glass wall protects the brain from the charger's power lines, but the communication lines have to go directly to the outside world, so they're fully exposed to the elements into ESD.
Right, they're just out there.
TVS stands for transient voltage suppressor. You can think of a TVS diode as an electronic airbag.
I love that. An electronic airbag that deploys in nanoseconds. How does a tiny piece of silicon act like an airbag?
It relies on a property called avalanche breakdown. A TVS diode is placed in parallel with the delicate communication wire connecting the wire to the electrical ground. Under normal conditions, when the normal 5-volt data is pulsing through the wire, the TVS diode is effectively invisible.
Because it ignores 5 volts.
Yeah, it has very high resistance, so the data just flows right past it. But the nanosecond, a massive 10,000-volt static spike, travels down the wire. The voltage exceeds the diode's specific breakdown threshold.
And what happens when it breaks down?
Its resistance plummets to near zero instantly. It essentially creates a massive open detour straight to the ground. The destructive energy of the static shock takes the path of least resistance, flowing through the diode and into the ground plane, completely bypassing the delicate communication chips.
Just shoving it into the ground.
Exactly. It shunts the overvoltage away in picoseconds. And the crucial detail in the architecture is the requirement for low junction capacitance.
Why is that important?
Well, if the diode has high capacitance, it acts like a sponge, soaking up the sharp edges of the normal digital square waves and distorting the signal, just like the fretting resistance we talked about earlier.
Yeah.
So engineers have to select diodes that are completely invisible to high-speed data, but capable of absorbing a lightning strike instantly.
Amazing. And what about the anti-bounce RC filter? You mentioned earlier that when the metal contactors close, they physically bounce, creating high-voltage sparks. Does the plug do that too?
Absolutely. When you push the heavy charging plug into the port, the metal pins don't just perfectly connect once. At a microscopic level, as you push, the metal surfaces scrape, connect, disconnect, and bounce against each other dozens of times over a few milliseconds before finally settling into a firm connection.
Like stuttering.
Yeah, and to the computer, that mechanical bouncing looks like a chaotic, rapid-fire machine gun of electrical noise. The computer might interpret that bouncing as dozens of separate plug-in events, which could crash the state machine software.
So how does the RC filter stop the machine gun?
RC stands for resistor capacitor. It's a low-pass filter. It allows low-frequency signals like the steady state of being plugged in to pass, but it blocks high-frequency chaos. When the pin bounces and creates a sudden spike of voltage, the capacitor in the filter acts like a tiny shock absorber. It takes a specific amount of time to charge up. So instead of the computer seeing a jagged, rapid-fire spike, the capacitor absorbs the spike and slowly releases it, turning the chaotic mechanical bounce into a smooth, clean, single, gradual slope.
Oh, that makes sense.
The computer only wakes up when the slope reaches a steady threshold, completely ignoring the microscopic violence of the mechanical connection.
So we have a soundproof glass wall using light, nanosecond avalanche diodes acting as airbags and capacitors acting as shock absorbers to smooth out the mechanical bouncing. The level of design prevention is astounding.
It takes a lot of work to make it seem simple.
Yeah. And we can't forget the software protocol juggling. The architecture notes that the car uses standard AUTOSAR software to flawlessly translate between different global charging languages, like the European ISO 1FETA118 standard, the DIN standard, and the Chinese GBT standard. It has to speak multiple languages fluidly depending on what kind of charger you pull up to.
Which requires incredibly robust state machine coding. It has to recognize the protocol, shake hands, establish the CRC parameters, and begin the translation, all while monitoring the 500 millisecond fail-safe window.
It is a true fortress. But here is the critical pivot. You can design an ASLD-rated 3,000-volt isolated optically coupled circuit on a computer screen. You can run simulations, and it will work perfectly in the digital realm, but eventually you have to build it in the real world.
Always the hardest part.
Right. You have human workers, robotic welders, and millions of tiny crimped wires. How do you guarantee that this perfect design actually translates to a flawless physical product when thousands of cars are rolling off a factory assembly line every single day? A fortress is only as strong as the bricks it is built with. Which brings us to the manufacturing side. The process, FMEA or PFMEA.
Yet, shifting from design to manufacturing is where theory meets the messy reality of mass production. In automotive engineering, you cannot assume that a part was manufactured correctly just because it looks okay. You have to verify the critical safety layers on every single vehicle.
The architecture outlines a few crucial tests that happen on the factory floor before the car is ever cleared for delivery. The first one is the contactor cutoff checking.
This is a direct, physical validation of the 500 millisecond guillotine we spent so much time discussing. They don't just flash the software, run a diagnostic check, and trust that the computer will tell the relays to open.
They actually test it.
They physically simulate a U019B communication fault on the factory line. They inject the error, and they use high-speed sensors to verify that the massive physical metal relays inside the battery pack actually spring open fast enough to meet that AZLD safety boundary.
Why wouldn't they open fast enough? If the software sends the signal instantly, what slows down the relay?
Mechanical reality. A contactor is a heavy electromagnetic switch. It uses a magnetic coil to pull a heavy metal armature against a heavy spring. If there is a slight defect in the manufacturing of the spring, or if the internal lubrication is slightly thick, or if there is residual magnetism in the core preventing the armature from releasing instantly, the mechanical action will be sluggish.
Oh, I see.
The computer might send the open command in 5 milliseconds, but the heavy metal plates might take 600 milliseconds to actually pull apart.
And if it takes 600 milliseconds, it misses the fail-safe window, and you risk lithium plating and thermal runaway.
Exactly. So the factory physically measures the mechanical flight time of the contactors. If that car's relay is sluggish, the vehicle is flagged, the pack is rejected, and it does not leave the factory.
That is rigorous. But the next factory test is the one that really highlights the ingenuity of process control. It is called the end-of-line, or EOL, Dynamic Contact Resistance Test, also known as the KCC test.
The shaker test.
Right. During this test, the factory connects a test cable to the car to simulate a fast-charging handshake. The car's computers think it's being plugged in. But while the communication data is flowing, the factory machinery actively and violently shakes the physical connector on the car. They vibrate it at high frequencies to measure microscopic impedance fluctuations.
This is a masterclass in uncovering hidden manufacturing defects. It is not enough to just plug a test cable in, verify the green light turns on, and call it good.
Because it might fail later.
Exactly.
Right.
A static test where everything is sitting still only tells you if the connection is good in that exact moment. But the factory engineers know that you are going to take this car out into the real world. You are going to drive over jarring potholes. You are going to vibrate down washboard gravel roads. And you are going to aggressively drag stiff, frozen charging cables through the snow.
So they're actively trying to annoy the car into failing before it leaves the plant. What exactly are they looking for when they shake it?
They are vibrating it at specific calculated resonant frequencies designed to induce the micromotion and fretting we talked about in the root cause analysis.
Oh, yeah.
They are hunting for hidden defects in the wiring harness. Inside that charge port, the heavy copper cables and the delicate communication wires are attached to the metal pins using a mechanical crimp.
A crimp is where they crush the metal barrel around the wire to hold it tight, right?
Yes. A perfect crimp uses immense pressure to cold weld the copper strands together into a solid mass. But what if the robotic crimper on the assembly line was miscalibrated by a fraction of a millimeter? What if the crimp isn't perfectly tight? Or what if one of the pins isn't seated entirely into its plastic locking housing?
In a static test, it wouldn't matter.
Exactly. If the car is sitting still, gravity and the stiffness of the wire might be holding that loose crimp perfectly against the terminal. The electricity flows, the CRC checkzones pass, and the static test says the car is perfect. But the moment you vibrate that port, that loose copper wire chatters inside the crimp barrel.
Oh.
The resistance spikes erratically. The square waves distort into shark fins, and the communication drops.
So by dynamically shaking the port while constantly monitoring the digital signal and the resistance, they can detect a micromillisecond drop in communication. If the impedance spikes during a factory shake, they rigidly intercept that car. They know that even if it works perfectly sitting on the factory floor today, that loose crimp will inevitably fail a year from now after driving over 1,000 speed bumps.
Precisely. They're forcefully compressing a year of mechanical wear and tear into a 30-second vibration test to guarantee the integrity of the physical layer.
Okay, so they've built the electrical fortress with isolation walls and airbag diodes. They've verified the mechanical guillotine and shaken out any loose crimps on the factory floor. But testing a brand new car in a clean factory for 30 seconds is one thing. How do automakers guarantee this incredibly complex microsecond safety net will still catch you a decade later after 300,000 kilometers of real-world abuse?
Right.
How do they know the fifth dimension won't just degrade and fail when you need it most? This brings us to the final and perhaps most intense phase of the engineering life cycle, the ultimate torture test, the design verification plan and report, or DVP&R. This is mass production validation.
Validation is arguably the most critical phase of automotive engineering. It is where you take everything you have theorized, designed, and built, and you dedicate months of time to trying your absolute hardest to destroy it.
Just beating it up.
Exactly. You subject it to conditions far worse than any human would ever encounter. If the system survives validation, it is finally ready for the public.
And the torture tests described in the architecture for the U019B fault are deeply brutal. Let's start with the HS simulator. That stands for hardware in the loop. What exactly are they doing here?
Before they even test a full vehicle, they take the physical battery management system computer, the actual hardware brain of the car, and they wire it up to a massive multi-million-dollar supercomputer rack. The supercomputer runs a real-time physics engine that simulates the rest of the car, the battery chemistry, and an external fast charger.
It's like the matrix for the battery computer.
It literally is. It simulates the voltages, the temperatures, the CAN bus traffic. The BMS computer genuinely believes it is sitting inside a real car charging at 300 amps.
And once the BMS is comfortable and thinks it's charging, the engineers start injecting poison into the simulation.
Exactly. The engineers forcefully break the simulated physical connection. The architecture states they deliberately inject 1.0-second communication timeouts. They randomly just cut the digital line.
Just to see what happens.
Yeah. And the strict requirement is that the BMS must detect the missing heartbeats. It must diagnose the U019B fault within that 1.0-second window, and it must command the failsafe and snap the virtual contactors open within the golden 500 millisecond window. And it must do this flawlessly, thousands of times, without a single kernel panic or software freeze.
They run this over and over, switching between all the different software languages, the ISO standard, the GBT standard, just to make sure the state machine software doesn't get confused and freeze up when the connection drops unexpectedly.
Right.
But as intense as the digital simulation is, it gets much worse when they move to physical vehicles. Next, they take an entire prototype car and lock it inside an EMI noise room, an electromagnetic interference anechoic chamber.
Yeah, an anechoic chamber is a massive room lined with metallic cones that absorb all electromagnetic radiation. It isolates the car from the outside world. Once the car is inside and plugged into a test charger, the engineers set up massive directional antennas pointing directly at the charging port and the battery cables.
And the specifications say they absolutely blast the car with high-frequency electromagnetic noise. They sweep the frequencies from 10 kilohertz all the way up to 150 kilohertz, bombarding the cables with up to plus or minus 8 volts of raw interference. They are actively trying to induce parasitic voltages on the communication lines to drown out the handshakes.
They're simulating the worst-case real-world scenario. Imagine pulling up to the cheapest, oldest, most poorly maintained fast charger in existence.
We've all seen them.
Yeah, a charger with degraded internal shielding that is just leaking violent RF noise everywhere. They replicate that invisible storm in the chamber. And the pass-fail requirement for this test is staggering. They demand a strictly 0% CRC error drop rate.
0. Not a single dropped packet.
0. Despite the massive antennas blasting the cables with 150 kilohertz noise, the galvanic isolation, the optical couplers, and the TBS diodes we explored earlier have to filter out all of that chaos so perfectly that the tiny 3-volt digital signal arrives immaculate.
Incredible.
If the noise manages to flip even one bit, and a single CRC checksum fails, causing a dropped packet, the entire electrical shielding design fails validation and must be re-engineered.
That is an insane zero compromise tolerance. But even that pales in comparison to the mechanical torture, the 10-year weather and wear test.
Oh, this one is rough.
This is the one that really proves how over-engineered these systems have to be. We talked about fretting and microarc oxidation wearing away the silver plating. To validate the lifespan of the physical port, they take a physical charging plug and socket and they hook it up to a robotic arm. The robot physically inserts and removes the heavy plug 10,000 times.
10,000 violent insertions. This accelerates a decade of physical friction. It guarantees that the wiping action grinds away at the metal, simulating the deepest possible mechanical wear.
But they aren't done. After the robot finishes 10,000 insertions, when the metal pins are thoroughly worn out, scratched up, and stripped of their protective coatings, they take that entire plug assembly and throw it into a climate chamber.
Yep.
They plunge the temperature down to negative 40 degrees Celsius, which is brutal, Arctic deep freeze conditions. Then they rapidly bake it up to 85 degrees Celsius, which is 185 degrees Fahrenheit. And they do this while injecting 95% relative humidity into the chamber.
They're creating the ultimate environment for galvanic corrosion and oxidation. The massive temperature swings cause the disparate metals in the port to expand and contract at different rates, forcing moisture deep into the microcracks of the worn pins.
And they leave it baking in that 85-degree, 95% humidity sauna for 500 hours straight, almost 3 weeks of continuous chemical torture on a mechanically destroyed plug.
And this is where the engineering really has to prove itself. Because after those 500 hours of extreme thermal and chemical abuse, they pull the plug out of the chamber and they measure the electrical impedance. The strict requirement is that the electrical resistance between the pins must remain below 0.1 ohms.
1/10 of a single ohm.
Furthermore, visual inspection must confirm there is no massive microarc blackening, and oscilloscope tests must prove there is zero signal distortion on the square waves. The RC time constant cannot have shifted.
Think about the scale of that for a second. 10,000 insertions. If you plug your car in every single day, 365 days a year, 10,000 cycles is over 27 years of daily charging. And even after 27 years of friction, plus being baked in an 85-degree, 95% humidity sauna for weeks to force catastrophic oxidation, the electrical resistance of those pins cannot fluctuate by more than 1/10 of an ohm. When a driver plugs their car in during a blizzard in Minnesota, or during a sweltering, humid heat wave in Florida, they don't think about contact resistance or galvanic corrosion or optical isolators. They just expect it to work safely. The physical robustness required to guarantee that mundane expectation is staggering.
It truly is. It represents thousands of hours of metallurgical and electrical engineering dedicated to anticipating every conceivable way the universe will try to break the connection. And the final step in the validation, the end-of-line 100% handshaking test, ties the entire fifth dimension together.
The arc flash prevention.
Exactly. They verify on a massive scale that the physical-mechanical lock actuator will never, ever release if the current sensors detect anything over 1 amp. No matter what digital noise is injected, no matter how the software is manipulated, the physical lock remains aggressively engaged until the physics of an arc flash are completely neutralized.
It is an incredible, invisible world that exists right there between your hand and the charging station. We've gone from the microscopic physics of electrostatic discharge blowing tiny craters in silicon to the relentless polynomial division of CRC8 checksums.
Quite the journey.
We've explored the chemistry of lithium plating that mandates a half-second software guillotine. We've visualized the 3,000-volt optical glass walls, the nanosecond avalanche diodes, the factory shake tests hunting for cold welds, and literally baking a mechanically destroyed plug in an Arctic sauna. Next time you, the listener, pull up to a fast charger, grab that thick, heavy cable and hear that heavy mechanical click, you'll know exactly what is happening in the shadows. You'll know there's a 3,000-volt invisible shield, a microsecond heartbeat doing complex math to ignore the noise, and an army of engineers ensuring that 500-millisecond failsafe is ready to protect you.
It really gives you a profound appreciation for the invisible infrastructure of modern high-voltage technology. The seamless user experience is basically an illusion bought and paid for by relentless paranoid engineering.
It really is an illusion of simplicity. But before we wrap up this deep dive, I want to leave you with a final, slightly provocative thought to pull on. Based on everything we've explored today about how fragile these physical metal pins actually are to the laws of physics, the fretting, the micromotion, the microarc oxidation, and the incredible lengths engineers must go to just to keep the resistance below 0.1 ohms, what happens next?
That is the big question.
Because the automotive industry is not standing still, they are aggressively pushing for even faster charging. They want 10-minute charge times. We are moving toward megawatt charging systems for commercial trucks. That means pushing twice, maybe 3 times the current, pushing the voltages well past 1,000 volts. That makes the physical stress, the thermal loads, and the electrical violence of plugging in exponentially heavier.
And the physical limits of base metals, friction, and oxidation are immutable. They are not going to change just because we want to charge faster.
Exactly. The laws of thermodynamics always win. So how will this invisible handshake need to evolve? As chargers become exponentially more powerful, will physical metal pins simply become too dangerous or too difficult to cool and maintain? Will we have to move to